Good afternoon, everyone. Welcome to the summer workshop on plasma physics, and I'm Swarni. So, today we are at our 16th lecture and we'll be discussing on the various problems that we will be carrying out in the project. Now, before we start, let's go to the list of projects. Let's start once again. How to read the assignment, that means how to deal with the problem. You see, you have got GJ set of equations with equation of state Pj like this, such as stretching and the perturbation expansion, and we obtain the accordingly dispersion relation of KdV and KdV Burgers equation accordingly, and finally get the results in a graphical way. Welcome to the problems once again, and remember one thing I have put here: those who will do only the KdV must eliminate the viscosity term in the momentum equations. Well, for this condition, keep in mind note 1 and note 2 who want to carry out numerical simulation study, they may carry out the study on the final equations as they like, whatever. You see, those who are doing simulations, it's up to you what code or what software or what language you will use. Is up to you, and how would you like to solve it. I considered that since you have opted for simulation studies, you know the simulation techniques, and you will be able to do it. As some of you have inquired, so what will you do it? I want to put a graph in Python, some say I do in MATLAB, some say it in C++, whatever it is, it's up to you and how you would like to solve it. Now these are the different problems. You see, 1 to 48 is just finding the dispersion relation. Okay, and we have done it. Let's come. Well, these are the governing sets of equation. Okay, so here you see you have been asked with the electron acoustic wave. Now, as in an electron acoustic wave, the hot electrons and the cold electrons are there, and for the hot electrons we do not consider the left hand side, that is the inertia term. Why? We consider them to be very mobile, such that the inertia effect may be neglected. But the pressure term or the restoring force is there, and since this is a quantum mechanical term, this will be included for both the electrons, hot or cold, depending upon the density. Now here, if you are asked for this cold electrons, you see the inertia term is there but not the pressure term. But here it's a viscosity. Those of you who will do KdV Burgers equation, they have to consider this viscosity term. Those who will do it this set of equations, suppose this G1 set of equation, only KdV equations, they just eliminate this. So those who will do KdV equation, for them the expression would be this one and this one, eliminating this part, and this will be the Poinsot's equation. For this we have our astrophysics and space science paper, how to carry out the normalizations. Now you see there are different kinds of normalizations. For instance, here we have a quantum term. These two are the quantum terms. Now this pressure you can take different way. Now if you take a quantum pressure, then you would get expressions like this pressure term. Okay. If you take relativistic pressure, you will get the degeneracy factor like this. Relativistic degeneracy pressure like this. Now you see we have simplified it, where ultra relativistic and weakly relativistic. So these are the two cases you will find in your project papers. You see, this is the pressure law. This is for the weak relativistic case, and this is the ultra relativistic case. Now you can just simplify it for you. Suppose you take this whole term, these are all constants, so it is equal to some constant. Suppose you call it a. So a n to the power 5/3. So you can start without writing this whole thing again and again, write it a n to the power 5/3. Now this is the unnormalizing. Now when you take a and you want to normalize it, because all these things are constant, if you want to normalize it, you divide it with nj0 for the hot electron or the cold electrons. Now these are the two expressions So you can get the reference here. And those who will be doing some other classical pressure, so there we will get pressure like this, P is equal to nkt, only for the classical particles. Remember why I said only for classical particles, because in many a problem you will find terms like this. Here the ions may be considered classical and the electrons may be considered quantum. So for the ions pressure you can take P is equal to nkt, it's up to you. And for the electron pressure you can take this kind of pressure or this kind of pressure. So that's up to you. You can make different combinations possible. Okay, now it's up to you how much you understand. Now coming to the different set of equations once again. Now someone asks, sir, in this ion acoustic mode, why did you put Qi? Well, in the literature you will find lot of equations written like this. So these are the Qi. What is the charge of the ion? You may put it Zi, where Z is the number of or the valency of the ions. Here Q is the electronic charge is equal to minus E. Whatever you take, make sure to use it throughout. And how to carry out the normalizations. Now you see, I give you a suggestion. Now here you have a quantum term. So the best thing is that you normalize it with the velocity, Fermi velocity of electrons. So you normalize velocity with Fermi velocity of electrons, and accordingly here as we have done the Fermi velocity with this term, and we have carried out the normalization. You see, x is equal to x omega pe. If you can watch it, okay, this is x is equal to omega p by VFE, Fermi velocity of electrons. Similarly we have Fermi temperature of electrons, we have used the temperature. So whenever you will get quantum terms, then throughout your paper you should, I would suggest, I would like you to take this kind of normalization, because that makes your problem very easy. Because whenever you are talking about something in the quantum range, and if you normalize it with classical velocity or classical potential, whatever it is, temperature, then it won't be suitable, because you have to have a set of equations where such a normalization is valid. Now someone asked me, sir, can we take a different kind of uh, normalization? Well, that's always possible, but you see, it should be also valid. So you are doing your problem in the quantum regime and you take a normalization in the classical regime, therefore that is temperature, thermal temperature we often call. So I would prefer to overcome this confusion and normalize with Fermi velocities. Number 2, for this I have given here. Now this is ion acoustic mode. Now you see, let me tell you, if you consider the only ion equations, so this equation and this equation, you will get ion acoustic modes. In ion acoustic mode, what will happen? You will just take the ions Ni as perturbation expansion, and for the electrons you can take a distribution function, as we have done in the last page. You see, you can take this kind of Q non-extensive distribution or kappa distributed distribution, or even Maxwell's distribution. Now that's up to you what you will take. Consider. Now you see, here the ion acoustic mode from here. Well, here for the ion acoustic mode, it is sufficient for you to take this equation, this and this. But provided when dealing with ion equation, you cannot this and this, the ions equations. So you don't take these electrons. But if you're going for electrostatic mode, remember, if it's electrostatic mode, then you consider both the ions and electrons. So take the 5 equations and solve it simultaneously. Okay. Now for a dust acoustic wave, here what are dust particles? Dust particles are suppose small grain of particles which attract electron on its surface. As a result, those particles become charged. So since those particles become charged in a plasma, they behave as a plasma particle, or influenced by the electric field, rather I would say, influenced by the electric field. So you need to have a set of equations, that is momentum equation and continuity equation for dust. You see, this is the dust continuity equation, dust momentum equation. Well, I haven't included here pressure term or a quantum term. Why didn't I include? Because dust are heavy particles. For them, this kind of pressure will be very negligible. And this quantum term, which is only for fermionic particles, so for dust, we don't consider those bomb term, bomb potential. Okay, for dust acoustic wave, you have 6 equations. Okay, now these are the 3 distributions, and this is the Poinsot's equation. So remember, it is given in the different mode. You should multiply it with 4 pi e if you calculate it in CGS method, whatever. But I want you to come out. Ultimately, it won't be a problem because that will be just a constant factor added up with the or multiplied with the whole set of equations. Okay. Now the pressure law, this is known as the Fermi pressure. So remember, whenever we are taking the Fermi pressure in your problem, you should normalize the whole set of equations with Fermi velocity, plasma frequency, and Fermi temperature. Okay. When you take this thing, you do the same kind of normalizations. And here, if you take only classical case, because all your problems are in the quantum regime, then I would say normalize all your problem with the Fermi velocity, Fermi temperature. Now these are the 2 kinds of stretchings that is possibly used. This is what we have used very often. This is another stretching that is important. Now this kind of stretching is applicable for plasmas in the critical regime. Now critical regimes are something which need to be studied a bit more. So those who will be doing this kind of stretching, please refer to critical regime in the literature. I will supplement it you with papers, and there you will find what are the stretchings used for. Now there are 2 kinds of perturbations. Here I have taken the normal perturbations for density, velocity, and potential, and here we have got another kind of stretching where you have used all the odd powers. Okay, so this is another kind of stretching, a perturbation expansion that you may use. Okay, now as I have said, in the ion acoustic mode or some of the other modes, if you are desirous to use, you can just use this kind of distribution functions. You will find some in the literature that these distribution functions can be expanded binomially to some extent of Q. Well, what is Qj? Qj is known as a Q non-extensive distribution function. So Q is an index, not a charge. Remember, Q is not a charge here. Q is an index known as a Q index. There are some statistics apart from the equilibrium statistics or Maxwell-Boltzmann statistics. Those are known as non-equilibrium statistics, and in such a case, Keynes distribution is there, Sally's distribution is there, and Sally's entropy is there. So a lot of different things. So as you start doing these things, suppose you are interested to know how to use this Q non-extensive, you select it, copy it, put it in the Google, you will get an idea what is Q non-extensive, what is Kappa distributions. These are all non-thermal distributions. Non-thermal, what is non-thermal plasma? You just check it. Okay, so whenever if people are using with this kind of distribution, their paper should have this term non-thermal or Kappa distributed particles, something like that. So I have supplemented with this Kappa distributions. You will check the papers. Okay, now Maxwell's distribution. Now coming to the different types of KdV equation, different types of wave modes. Sorry, you should. You see. Well, this was an amplitude modulation. So we are not doing this because some people who will finish this part of the assigned project first, if they are desirous to go into the astrophysical plasma section, then they will study the raw waves. So for that, a next lecture will come how to study the raw waves. What are raw waves? Like a tsunami. You know, tsunami is a very raw wave with very high amplitude and much energy. So in astrophysical plasma also there are this kind of wave modes, so, Rog waves. So for Rog wave you have a different kind of transformation to be used at a later part. Well, we will come later. Now I will just suggest you with some more articles. Now, well, what is ion acoustic mode? As I have said few times back, it is ion acoustic mode. Well, here in one of our papers, you have ion acoustic mode. So, as I have said, you only consider the equation of ion. You see, continuity equation of ion, momentum equation. You have got the pressure here, and it's the Poinsot's equation. So here, when we went there to the ion acoustic mode, what I said, if you want to study ion acoustic mode, so those who have got this option G2, they can either start ion acoustic mode by neglecting the electron equation of motions, only taking these two ions and the Poinsot's equation. So that will give you ion acoustic mode. Okay, and those who are interested to study the electrostatic mode, please take the 5 equations. So you get an additional choice. Okay, those who have started doing it G2 or group of that is governing equation set 2. Now come on, so these are the basic set of equations. You will find that paper that I have studied is in or I'll just send, if not this one. So you see here we have taken a classical pressure. Very good. We have taken a classical pressure because there is no quantum term, you know, there is no bomb term, quantum diffraction term. So no need to bother about. We can easily take it, the ions to be following classical pressure. So if any of you are interested to eliminate the bomb term, if you are not comfortable with it, you may eliminate and then take this pressure. It's up to you. Okay. So you get these things, and finally you see what he has done. He has taken the particle density and have put it in the normalized set of equation, or normalized set of equations, and in the Poinsot's equation they have just substituted this thing, you know, Ni, Np, Ne. You see Ne is the electron density. Well, it was a non, it is somehow, you see, this one is the Maxwell's-Boltzmann distribution. Now this is an additional part. Okay, so this is the non-thermal part. You can also take this kind of distribution if you want, a lot of things. So that's why I've given some more particle distribution, and if you are interested, while you take, just make me a call if it's possible. You want to verify it. Okay, so this is the equation, and then you get the perturbation expansion, the dispersion relation, and after that you take similar stretching. You see, you have taken epsilon to the power of epsilon 3/2 and get the KdV equation. So there was no KdV Barger's equation, so it's good that you don't have that resistive term minus R. So those who will be doing with that KdV Barger's equation right here, then they will have on eta I del 2 ui del 2 vi by del xi2 after normalization, del x2. After normalization you will get this. So it is not unnormalized. So this paper we haven't put normalizations. Well, now those who will do about the dust acoustic wave, you see, this paper I have sent you. Equation of motion, you see, two equations, and finally the Poinsot's equation. Now you take this kind of perturbation expansion. You may change your perturbation expansion as well. You see, we have given you that option to do it. Okay, the velocity and the densities, they have got this kind of perturbation expansion, and they have taken the epsilon to the power of epsilon to the power 3/2, and well, it's a, I don't know what kind of journal it is. Anyway, we are taking the calculations, and they have put this boundary conditions. You can also use, now whatever you use, if you are taking the dust acoustic wave or whatever it is, take help from this paper. Okay, So you get the KdV Burgers equation, no, KdV equation, because there is no shock wave, so they haven't done here. Now if anybody of you are willing to go for the shock wave kind of thing, that is, if you have that viscosity term, you see here you have got the viscosity term for cold cold electrons, okay, and hot electrons, they do not have the viscosity term, and also they do not have the inertia term. So what happened, they have taken it, and what do you suggest? Will we get a KdV Burgers equation? Yes, we'll get a KdV Burgers equation. You see, this is the Burgers term, and if it is only Burgers equation, then this dispersive term, B wala term, won't be there. Okay, it will be absent. So it will be KdV. This is now a KdV Burgers equation. If this one is not there, B is 0, so it is Burgers equation. If C is 0, then it's a KdV equation, and if you have all these three terms, it is KdV Burgers equation. So nonlinear term will be always there. Okay, and well, so we can just understand now, revamping all our set of equation once again. Sorry. So governing equations, it is ion acoustic mode, it is electron acoustic mode for governing set of 1. For governing set of equations 2, G2, it may be ion acoustic mode or maybe electrostatic mode. You see, you will find ion acoustic mode or you will get electrostatic mode. Okay, fine. Governing set of equation is dust acoustic mode. Okay, and in a plasma, if suppose you eliminate these ion terms, suppose your dusty plasma is formed of electrons and dust particles, then these ion terms won't be there. You can also have a option, if you are thinking that you can choose your own problem, or you can just uh, improvise it, you can just eliminate these two ion equations, so that becomes a dust acoustic mode, where and this ion term won't be there. Okay, provided this charge would be then opposite to electron charge. This is electron charge. If it is Q, if it is E, or if it is minus E for electron charge, it should be some plus Zi, Ze. Okay. Okay. These are the two pressure laws. This is the Fermi pressure. This is the weak relativistic degeneracy pressure. It is the ultra relativistic degeneracy pressure. And these are the classical pressure for if you take the ions to be classically followed. So these are this kind of stretchings. Now the question is, these are the distributions that some use. Now there were some questions regarding the gamma factor in the velocity, in the momentum. Now you see, if you want to modify your equation, okay, if you are happy with that gamma term, you can just put a streaming. Whenever you have this UD, here UD, you just modify it with gamma. Okay, how? Let me check. Let me show you. Here what I asked you, here what I asked you, okay, here I said you can include relativistic streaming effect. So these equations must be this UD into gamma, and this would be UD into gamma. Similarly UY, not this UY, but this UY and this UY must be multiplied by gamma I as well as gamma E. How? Let's check here, as we have done in the Pramana paper long time back. Yes, you see, these are the gamma terms that we have used. So you can just improvise your problem. I think that will be quite helpful for you. And as for the allocations, how you have performed in the allocation, you see, just well, These are the groups. Majority of you have applied for KDV and KDV barges. Only few have started with this pseudo potential. Shubhadeep De, Shaurodeep Thakur, Sneha Gayan, and no more. Well, I expect you people, those who have opted for Sagdi's pseudo potential method, is very easy. Suggest some books. I will suggest some lectures and how to carry out. And the technique is very easy. You have to plot the Sagdiv pseudo potential and you can get different kind of you see, once you obtain the Sagdiv pseudo potential, you obtain the expression for Sagdiv pseudo potential like this. Now applying certain factors, boundary conditions. What are those boundary conditions? So how to find the solitary wave solutions? You see, at n is equal to 1 and n is equal to nm, un is equal to 0. So you take the derivative, you take the second derivative, and for that point you will get to you get an expression in terms of xi and n, and you can just plot it. Okay, xi n versus n is the density versus n. You can just do it. For that, I have also suggested you with a paper. We'll see. Shah and Manta, Om Prakash Shah, I think. They have carried out this Sagdiv pseudopotential approach, and these are their pseudopotentials, you see. And they have got this kind of solution for the plasma parameters phi. It is getting a change, you see. It is rarefactive soliton, then it's become a compressive soliton, and you can do it. We can get soliton structures like this, so that's also possible. These are the fluctuations. What are fluctuations? I think they have corresponding fluctuations and not in the field potential. Yes, in the potential field they have got this thing, and this is somehow related. You have to just check it. That is, they are not forming a solitary structure, but an oscillatory kind of solution is there. Okay, these are fluctuations, and this is when these fluctuations add up, they give you a solitary structures, stable rarefactive solid, stable structure, and these are fluctuations. So I think you can just do it, and it's my pleasure to check. And those who have taken Sagdiv pseudo potential, I hope you will get more interest if you study a bit more on solid pseudo potential. Now, one more thing, I will also submit some of the okay. Now I have submitted in your lecture this how to deal with the step by steps. It is written how to deal with the KdV or KdV-Burgess equation. You have to use the perturbation technique. You see, reductive perturbation technique. What we are doing, these are the equations. We use the reductive perturbation technique. Now substitute, or in the first order terms we get NV relation from the continuity equation, and from the higher order equations we get V2 terms or N2 terms, whatever it is. I think it's clear. You see, from the momentum continuity equation first order term, you will get relation between density velocity. From the first order momentum term, you will get a relation between velocity and potential, and in many cases you can also get relation between density as well if you take the pressure term. And from the second order term you get from Ni2, that is second order perturbation in density, velocity or relation, and from the potential. So eliminating all those terms, you come all in terms of the first order potentials, that is phi 1, and you get a KdV equation. Now higher order terms considerations, well, a lot of people do higher order considerations, not only constraining themselves in the first and second order, they go to the higher order, and what they get is the modified KdV equations. Modified KdV equations using reductive perturbation technique. So you see, these are the different forms of modified KdV. So we know this term, we know this term, and we know phi del xi. That is, till here it is our known. This one, suppose if we eliminate this term, this is our known KdV. This is addition of higher order term, so it is a modified KdV. Here also these two terms are from known KdV, these two terms are additional terms. Here it is our known KdV, but this C phi 1 term is the additional term because we have considered the higher order terms. So we get a modified KdV. So those who have done KdV and you are thinking what to do more, you can just go to the higher order and get a modified KdV. So that is also a part. So as we have obtained this KdV part, just modified KdV, blah blah expressions, we will use our solutions. As we know, what kind of solutions? You see, what kind of solutions? We know this sec hyperbolic square solution for KdV and sec hyperbolic and tan hyperbolic for sec hyperbolic and tan hyperbolic for this is the for the solitary wave and shock structures. If you want to study only the shock structure, eliminate this part. Only this one would be the for the shock structures. And when you plot it, now next comes the plotting. How to do the plotting? You may use MATLAB, you may Desmos, or you may use anything, whatever, Mathematica. Even you can use Excel, whatever, if they support your geometric or mathematical scientific calculations. So you can just use your available resources and plot graphs for the dispersion relation omega curve plot, and for the solitary structures you have a plot of this phi versus xi. Here it is psi, written psi. It is the phi versus xi or eta, what you have often written here, eta. So that's how you can do it. Just study a bit. Okay, thank you.